Okay, yeah, thanks everyone for coming. We're very happy to have Fernando Romero-Lopez to be our speaker today. Fernando did his PhD in Valencia University, and he's now a postdoc at MIT. And in this summer, he will be joining the University of Bern as a new faculty. And he has worked on a variety of topics, including large N-C physics, also developing formalism for multi-hadron states, and also implementing this formalism in actual lattice QCD calculations to calculate scattering for different resonances and unstable states. And he has also been working on using normalizing flows and machine learning techniques for lattice QCD. And he is a collaborator of mine, Andres, and Rules in various different projects. So we're very happy he's here, and we hope he comes to visit us again soon. So yeah. Take it away, Fernando.
Yeah, thank you very much, Dimitra, for the introduction, and everyone for having me here. So today we'll be talking about hadronic resonances again. We already had a very nice one yesterday, but I think this is kind of fits in the discussion. Okay, so
Register the critical slide again.
Yeah. Now it's working. Good. Just a little slow, so sometimes it won't match what I'm saying. Okay, so QCD is this beautiful little theory of everything that we have. It's extremely simple to write down, as can be seen by the QCD Lagrangian. It has, however, very deep implications for nature, and most of them stem from the phenomenon of confinement, the fact that we can't observe quarks and gluons freely, but rather in the form of pulsate hadrons. This gives rise to the hadron spectrum, which is this set of all the experimentally observed hadrons that we have. In the hadron spectrum, we can differentiate two kinds of hadrons. One of them that we consider QCD stable hadrons. Those are typically the pseudo-Goldstone bosons of the spontaneous chiral symmetry breaking, like the pion, the kaon, and so on, but also the proton, the neutron, and other kind of baryons. Those are states of QCD. If we consider the QCD Fock space, we can have pion, kaon, proton states there. These hadrons are typically more or less well understood, both from the experimentally, but also theoretically. By contrast, we also have other kinds of hadrons, those that are sorry, unstable. The resonances. Oh my god. Okay, now, sorry, I'm still learning how to use this pointer. We also have these other unstable hadrons. The resonances, they typically show up in scattering processes. For instance, this example here, where we have, you can just kind of see it. The example here where we have an experiment where we have a pion hitting a proton, and then we have a bunch of particles in the final state. And if we focus on the two pion invariant mass, we will see like this narrow peak here corresponding to the rho resonance. This is the signature of unstable hadron, and those are hadrons that are not states in the QCD Fock space. And this is the particles that typically we don't understand as well as the QCD stable hadrons. In fact, the hadron spectrum is still growing. It's ever growing. In the last decade, we've discovered many different hadrons experimentally. This is a plot from LHCb, and you can see here all these recently discovered particles. They are, or some of them are, in the category of unconventional hadrons or exotics, in the sense of that they are not described by meson, like quark and quark, or baryons, like three quarks, but for instance, are pentaquarks or tetraquarks and so on. One of them that I wanted to highlight is this one here, the doubly charmed tetraquark. It's one of the latest that has been discovered. It's a tetraquark that has 4 different quarks in the valence sense, and it decays to 3 particles dd pi, and I will be coming to this particular state or hadron at the very end of this presentation. So understanding this, the hadron spectrum is a really interesting question from the QCD perspective, but beyond reasons that are just QCD, describing resonances is important, for instance, if we care about like beyond the standard model of physics. In particular, hadronic backgrounds appear in many of the experiments that are conducted globally. For instance, if we're looking for CP violation, and it's a particular place where people are interested in finding signatures of beyond the standard model of physics, we will see that interesting measurements are in the realm of hadron physics. For instance, a decay of a kaon into 2 pions, leading to this epsilon prime over epsilon, or the decay of a d meson into kaons or pions, which was actually confirmed to have CD violation within 5 sigma just a few years ago at LHC. happens that the decay of this heavier hadron to the lighter one has about the same energy of some of the hadronic resonances. For instance, the sigma resonance that Archides described yesterday is in the vicinity of the pi-pi final state, and the F0 resonance, one of the F0 resonances in the vicinity of the KEK or pi-pi final states in this meson. Moreover, in neutrino physics, we have this neutrino-nucleus interactions that are relevant for experiments like Dune or HyPK, where we have a neutrino that hits some nucleon and has the energy that is large enough so that nuclear or baryonic resonances can be excited. And this is a particular plot from a review where you have here the momentum transfer and the center of mass energy. And the moment that the center of mass energy of the hadronic final state basically hits 1200 MeV, then you can excite the delta resonance, but also at some point many others. So if we want to understand or control these hadronic backgrounds, we need really first principles understanding of QCD resonances. Okay, so the tool that I like to use when there's questions about hadron physics and QCD at the low energy regime is lattice QCD. So this is a lattice QCD talk, therefore I have to have the canonical lattice QCD slide, but I hope not to get too technical. So lattice QCD is a first principles approach to the strong interaction. It is based on the path integral formalism with the several ingredients. So first we compute, first we formulate the theorem on Euclidean spacetime. This gives us, or this turns these exponential factors here in the path integral to real numbers, and this kind of lets us formulate all this lattice field theory machinery in terms of statistics. Then we take, our theory, which is given by the Euclidean action. Now we formulate it on a space-time grid where we have our fields as well as our interactions. And we have now a finite number of variables in terms of finite number of space-time points. And once we have all that, we can then use Monte Carlo techniques to sample correlation functions. And correlation functions are objects like this form here, where we have some operator that creates particles or states and so on. These are estimated stochastically, basically using Markov chain Monte Carlo techniques. So the question that really is relevant for this presentation today is whether we can obtain resonance properties or the properties of these unstable hadrons using lattice QCD, that is using Euclidean correlation functions. And of course, the answer has to be yes, otherwise I wouldn't be here giving this talk. And I will explain why it's yes, but not that simple. So let's think about experiments and how resonances emerge in experiments. Typically, scattering is defined as a real-time process where we have some asymptotic states that are far away from each other that are thrown into a region where they interact, and once they interact, we measure in our detector what comes out. So coming back to the same plot I showed before, we think of a pion hitting a proton and creating a bunch of other pions in this detector. And then what we measure is nothing else than the number of events or the number of counts per bin of energy or invariant mass or something like that. And this is something that gives us access to cross sections and indirectly also to scattering amplitudes. Now, this is experiments. This is the real world in some sense. But in lattice QCD, what happens is significantly different. We are forced to formulate our theory on a finite box, and this box is Euclidean time. So there's no notion of time evolution in the Minkowski sense, in the sense of real time dynamics of scattering. But also we don't have asymptotic states that are far away from each other. So the only thing that we have is stationary states in a quantum mechanical sense. So we have to make sense of how to connect these two worlds, and this is what the so-called finite volume formalism, which was started by Lucian in the 80s, gives us a bridge between the finite volume to the infinite volume. Okay, before getting a little bit more technical, let me just say, perhaps slightly more mathematical, what I mean. What we want to do the research line that concerns this is trying to map or trying to constrain the scattering, the matrix elements of the scattering matrix, the S matrix, using lattice QCD. So we have some incoming states, the S matrix operator, and some outgoing state, and we want to constrain those entries using this technique, lattice QCD. The reason why this is interesting is that if we have information about these matrix elements, we also have information about the resonances, the unstable hadrons, and in particular, unstable hadrons resonances manifest themselves as poles in the complex plane of these matrix elements here of the S matrix. So if we have here, there's nothing else than a pole taken from the PDG. This blue line corresponds to real energies, that is where we have access in experiments or also in lattice QCD. And the manifestation of unstable hadron is that pole, that infinite, that is slightly off the real axis. And position of that pole. The real part tells us the mass of the unstable hadron, and the imaginary part of that pole tells us the width of that unstable hadron. So in a cartoon sense, what we want to do is this thing here. We prepare some incoming states, some outgoing states, and these little explosions there is telling us the matrix elements of the S matrix. And in those little explosions there is where we will have, in the complex plane, the resonances that we care about. Like the delta will appear as in pi n to pi n scattering, or like the Roper, which can appear in pi n or pi n to those systems. Okay, so this concludes my introduction. In the remaining of the talk, I will first tell you a little bit more about how to extract scattering amplitudes from lattice QCD. Then I will show you some results for meson-baryon scattering. And then finally, I will discuss three-particle systems using lattice QCD. Okay, so let's go to the first part, which deals with scattering amplitudes from lattice QCD. This works. Okay. Okay, so before discussing the detail of each part of this strategy, let me just give you an overall picture of how scattering amplitudes are obtained in general from lattice QCD. And then I will go into each of these steps individually, trying to go into more detail. So the first input will be the spectrum. This is the set of energies that are obtained from Euclidean correlation functions. And this corresponds to basically putting QCD on a box, on a finite box, and so on, obtaining the energy levels. Once we have these energy levels in a finite volume of QCD, we will map them, or we will use the so-called quantization condition. This is the finite volume formalism initially developed by Lucier, which basically serves as a bridge between the finite volume to the infinite volume. This comes in this form of quantization condition that I will explain a little bit. Thus, this formalism basically gives us access to what we call infinite volume scattering quantities. These are some mathematical objects that receive the name of K matrix, phase shift, or scattering amplitude, but this is basically all equivalent or different ways to describing the scattering dynamics of particles in infinite volume. And once we have this scattering or this infinite volume scattering quantities, we will go into the complex plane. We will analytically continuate the scattering of this complex plane to find poles, which means finding zeros of the inverse scattering. Okay, so this was just an overview. Now let's go into each of these steps.
First time, this kind of quantization condition.
Mm-hmm.
So what is F and?
Yeah, two slides. I will come back to these in 2 slides.
Okay.
That can ask you.
Yes.
So the spectrum, the energy level, how many you have to infinite?
Yeah, I will show you in a bit. So this was just an overview to lay out all the points, and now let's start with spectrum. You will see that in a minute. Okay, so energy levels from lattice QCD. This is the input of all these scattering calculations. The idea is we construct correlation functions of operators that are put in some different time slices in Euclidean time, and that have some Euclidean time separation. If you perform a spectral decomposition of this Euclidean correlation function, you will see that it's given by an infinite sum of exponentials with some positive coefficients. And in the exponent here, we'll have the energies of the system, all the spectrum, all the possible states that have the same quantum numbers as the operator. You can already guess what is a way to obtain at least one of these exponentials, and that is the following. If you take the two operators and you separate them away enough from each other, all these exponentials basically will die, except of the one that falls out the slowest, which is the ground state. So this idea is Euclidean correlation functions can be mapped into at least the ground state of the theory with the same quantum numbers as the operator. Of course, typically you want more than just the ground state of the theory. So what you do, without entering many details, is you construct matrices of correlation functions. So you use several operators that have the same quantum numbers, but that look different, or that are constructed differently in terms of the quark fields or gauge fields. And then you solve the so-called generalized eigenvalue problem. It's kind of like a diagonalization of this matrix of coordinates. And this will give you access to the spectrum. And just to give you an idea of how this typically looks, imagine that we have two positive pions, so operators that have the quantum numbers of two positive pions. Something that I should say is that in lattice QCD, we don't need to work in the case where the particle, the quarks, have the mass of the physical quarks in the real world. We can tune them to be slightly heavier. And in fact, we frequently do it because it's cheaper, computationally cheaper. So in this case, we have 200 millipions. And now each of these points here corresponds to one energy level obtained from lattice QCD that has the quantum numbers of that. And for now, don't worry about these labels. These are just some finite volume labels. Okay. So spectrum is obtained from correlation functions using several operators that have the same quantum numbers. Now, what do we do with these energy levels? And this is when
I'm sorry,
yes.
I missed the one. How do you get, I mean, I know you get the ground state energy level. How do you get the other energy level?
Instead of using a single operator, you use a matrix of operators. So you have like operator 1, operator 2,
You have
operator
different
3,
operators.
different operators, and then you put them and you construct matrices of correlation functions.
But how do you know the operator corresponding to the same different energy level in the same operator in the composition?
The energy.
This is a series like energy 0, 1, and
if the operators have the same quantum numbers are things like isospin and things like that. If the operators have the same quantum numbers, they couple to the same energies. They couple to the same energies, but they have different couplings to each energy. And you exploit the fact that each operator.
But the operator is different.
The operators are different, yeah.
Yeah, so that's why maybe I need to learn a little bit more. How come the different operator have corresponding to the same energy level as when you do this composition?
Because they have the same quantum numbers. If
I know
two operators have,
even though they have quantum bits, that's proof that if you have a given quantum number, you can prove this is the same.
right. I mean, this is just selection rules of standard quantum mechanics, right? If you have a state with some quantum numbers and an operator with a quantum
But you have
numbers.
different quantum number. That's the problem. You have different quantum number.
No, the same global quantum number.
The same global quantum numbers,
So then
like
you have
isospin and things like the finite volume equivalent of angular momentum,
And then you have
parity. Sorry.
You have
I was just pointing
Okay.
that this way, you look at it vertically, given a quantum number.
Yeah, given a quantum number, you have this energy.
It's a tower of states,
then you can prove you have
excited
a
states.
transfer.
But then you have different. Is that different operator? or
This is
not?
like different quantum numbers,
Oh, the different quantum.
finite volume quantum numbers. Yeah.
But once you set that up, then you can prove you have a transfer operator. And so the spectrum is independent of the operators you use.
So actually,
Thank you.
it's like interpolating, as long as there's any overlap with the state that you want to see will show up. Like if it's too small, you won't see it.
Exactly. It could be too small, but in principle, all the states with some overlap shows up. Okay, so now we have these energy levels that we obtained from these correlation functions, and we have to make sense of them, right? So now let's take a step back and think of quantum mechanics. Like when we put some particles in a box with periodic boundary conditions. Because of the boundary conditions, what happens is that the particles are restricted to have some quantized values of the momenta. So if we consider a box of size L, the momenta that a particle can have in a finite volume with periodic boundary conditions is 2 pi over L times integers. Now, so if you consider two particles in a box with these periodic boundary conditions, a free scalar theory will tell you that these are the allowed energy levels that you can have in a discrete, in a finite volume. Now, this is just a free theory. Of course, QCD is an interacting theory. So what happens is that you have to turn on interactions. This also is something that we learn in quantum mechanics. That is, when you have an interaction Hamiltonian or when you add interactions to a system, energy levels move. And in particular, you can calculate this, for instance, in perturbation theory. So if you think about the ground state of two particles in a box, it's just 2 times the mass of the particle if the particles are identical. This is the free theory, but if you add interactions, what happens is that there is a correction to the energy of the system that is basically proportional, at least at leading order in perturbation theory, to the matrix element of the interaction Hamiltonian. And turns out that you can relate this matrix element of the interaction Hamiltonian to the scattering amplitude at threshold, at least to some power in the volume. So what this is telling you, this simple exercise in quantum mechanics, is telling you that the energy shifts that two particles experience in a finite volume is related to the interactions of the theory, is related to in particular to the 2-to-2 scattering amplitude at threshold. This is a very simple exercise based on perturbation theory, so in reality this is significantly more complicated, and it is a problem of putting a generic quantum theory into finite volume. So what is the solution of putting this quantum field theory into finite volume? And this is what this two-particle quantization condition, or where this quantization condition appears. Okay, so this is the finite volume formalism. This originally developed by Lucier in the 90s or in the 80s. That serves as a connection between the energy levels in finite volume to the infinite volume scattering. Okay, so this is the central equation, the two-particle quantization condition, that is a determinant equation. And every time this determinant vanishes, we have a solution in finite volume. That's why it's a quantization condition. Solutions means energy levels in finite volume. Now, there are two parts here of this equation. The first one is the scattering K matrix. This is an infinite volume quantity that is related to the interactions in infinite volume, typically parameterized in this form, in different partial waves, and given in terms of the phase shift. It's just standard scattering phase shift. Now, at the other side of the integral of this quantization condition, we have some kinematic function. I'm not giving you explicitly how it looks, but all I'll tell you is that it contains the information about the finite volume. And in particular, it looks like basically the sum minus integral difference of an object with a propagator. And this thing, if the volume is infinite, a sum and an integral are the same, so it's 0. But if the volume is finite, you will have finite volume effects in this, coming from this finite sum minus integral difference. Okay. So what this determinant equation tells you is the connection between K matrix or scattering amplitude to the finite volume. Okay, this is not general in the sense of like it doesn't apply to all possible systems, but it only applies to two particles below inelastic threshold. So where you can have 2 to 2 scattering, only 2 to 2 scattering processes. Okay. So let me show you in practice how this works. Okay, so if you consider two pions, which are scalar particles, where only S-wave interactions contribute, this is a simplification, you're neglecting interactions of higher partial waves, the quantization condition becomes this simple algebraic equation. The determinant goes away, well, it's rather a simple determinant in a 1-by-1 matrix, so it's just algebra. And this is basically telling you that every time you have an energy level, so every time you have an energy obtained from finite volume, you can take this equation and map it into the phase shift, or map it into the K matrix, which is ultimately related to the phase shift. So basically, in this simple case, each time you can measure an energy level from finite volume, you can measure a value of the phase shift in a particular energy evaluation. So if we come back to this plot that I showed you before, these are energies obtained from lattice QCD. These are again just some finite volume quantum numbers. Don't worry too much about it. What happens is that each of these energies can be mapped into a point in the phase shift. For instance, that energy there in orange here corresponds to that particular point in the phase shift as a function of momentum curve. And then you can take all your other points, like this one here, and map it there, and this one there, and map it there. And ultimately, you map all these energies into all these points, and you have a constraint on the phase shift as a function of the energy.
But on the left, I have now two different states, and on the right, they're sitting on the same state. So what's going on? Right, I have the A1, whatever I can read, is the yellow ones. They have different quantum numbers, lattice quantum numbers, and on the right-hand side, I have only one quantum, the same quantum.
Right, so this is, so for instance, this orange and this one red,
Yes.
they have slightly different quantum numbers on the lattice,
Yes.
because they have different total momentum of the system.
Okay.
But the mapping between this mapping here is still holds in that particular case. So this is quantum number dependent, so it's not as simple as this, but in principle, each energy level has some quantum numbers, and those can be mapped into basically partial waves in infinite volume. So finite volume quantum numbers can be mapped into infinite volume angular momentum in some particular way using these formulas. But it's not one-to-one. Sometimes there's like complications, but that is the general idea.
So from left to right, you suddenly get uncertainties.
Sorry?
So from left to right, you suddenly have uncertainty, error.
Right. So like you see this, the uncertainty there is like this thing,
Okay.
and that is mapped into that uncertainty there. What I'm not showing you is the uncertainty on the best fit, but that exists too.
So I don't see very well. Is the uncertainty on the cotangent of delta shown by bars that are not fully vertical?
Yeah, they are not fully
Uncertainty in the
vertical.
energy.
It's hard to see, but they are not fully vertical, and this is because of this equation here has like a nonlinear mapping, and therefore, like you observe this like tilted pair of bands. Yeah. Okay, so just another example. I'd like to show this in particular in front of one of the authors here, our guides, who gave a talk yesterday. And this is how lattice QCD results on scattering amplitudes can actually be very useful to complement experimental results. So this is plot here showing the P wave scattering phase of pi k scattering as a function of energy. These points here are experimental results, and these are here analysis using dispersion techniques, dispersion relations that we heard of yesterday. Now we have here results for experimental measurements of the scattering phase only at high energies, and in particular, basically all of them are beyond 1 GeV, right? And where we have experimental results, we see that the phase of the scattering phase is negative, which means that the interactions are slightly repulsive. Now, there's this particular or interesting phenomenon here is that at some point, the analysis or the dispersive analysis tells you that the phase shift is going to change signs, and it's going to turn from slightly negative to slightly positive, and then ultimately come to 0. That's a constraint.
Without Coulomb?
Sorry?
Is that without Coulomb interactions?
This is without Coulomb. I think this is just experimental measurements. So this is really experimental.
With Coulomb.
Actually,
So it's just fit to the experimental data.
Okay, so it has
the
Coulomb in it, right?
Yeah, it has everything that the experiment measures.
Okay, so we have, they have this analysis tells you that it's attractive at threshold. However, you don't have really data to see that there. You can only infer that based on fits and theory. However, lattice QCD actually can access that region, and this is the region where we actually can do the best job in lattice QCD because it's the elastic, the region where we have only elastic scattering. And in particular, we do that. We study scattering process, like doing the same process I showed you in a few, like last slide, and you can compute the scattering length of the pi k system in the p wave, partial wave. And these are these results here, where the sign is matched so that positive corresponds to positive on this side and negative corresponds to negative. And what we observe, there are several results. Our results are this one in red, Hadspec collaboration obtained this one in green, and slightly heavier masses. Is that for the cases where we have studied the pi k scattering, p wave scattering length, we actually observe that it is attractive at threshold. So we do see this attractiveness behavior, even though we don't have experimental confirmation of that. So this is kind of a synergy between lattice QCD and experiment that is exploited in many cases, or can be exploited in many cases.
What's on the x-axis? This is what, m pi?
M pi over f pi. This is just m pi.
Oh, so this is one fixed momentum.
This is an ensemble, lattice QCD ensemble. So here is like 200 MeV pions, 300 MeV pions, 400 MeV pions.
Yeah, but if I want to compare this with the left plot.
Yeah, the left plot, you see the blue point there?
Yes.
That is like the scattering.
Okay, so it's like a very, okay.
Oh, that's
So this blue point is the same that basically marks the final points up there.
And the lattice doesn't have Coulomb actually.
No, it does not. It's just QCD.
this is a function of like what?
Biomass. Scattering length is a function of the biomass. This is physical point experiments.
The last point is the physical point. Right?
It's experiments. So it's like this, it's dispersive analysis. It's analysis of experimental data of the real world. And this is lattice QCD predictions for a different bias of the biomass, of course. Quantitatively, it's not expected to be identical because the biomass is different. But qualitatively, you can see that it has the feature of being attractive at threshold.
But you don't have the data to the very low energies on how do you use
because this is experiment. This is not what goes.
I know that's experiment, but that point corresponding to what?
This is a function, right? This is a function which is this thing here is the phase shift as a function of energy, and the scattering length is defined.
But you don't have data at that point. I mean,
but you can still fit that to that and obtain it. Maybe one of the authors.
So you are very confident at your extrapolation, to that level, right?
This is not mine. This is an analysis of dispersive. This is his actually.
There's actually I should say a couple of words of that. So you see two bands there to the left. So you see an orange and a gray one. I don't know if you see like the orange because it's underneath.
Yeah,
so the orange is just the fit to the data, and of course the threshold is extrapolated.
Yeah, I'm saying that you are very confident at the extrapolation to that level.
I am not really confident about the orange one, and I am not 1,000% confident about the gray one, but it's better in the sense that the low energy region of the gray one doesn't have any data, but it does have constraints coming from crossing symmetry, from dispersive relations and rules. So there are these integral equations, which inputs are dominated by other partial waves that do have more input at low energy, and they give us a number for the scattering length, which is what Fernando is quoting. Yep. So when you impose that set of dispersion equations, then is when you see that this gray band bumps up and becomes positive. So it's not dominated by data in that partial wave, because you have this cross symmetry is dominated by data in all particles at the same time. So it gives us better constraint.
But the point is, you don't have data here, but lattice QCD can tell you what the scattering length is, and what we see is consistent with the prediction based on.
I mean, your confidence is not coming from data.
My confidence is coming from my lattice QCD calculation and agrees with their results based on dispersion.
If some of our experimentalists would be listening, maybe they are listening on Zoom. In principle, in heavy ions, you could explore this, right? The final state direction femtoscopy. I don't know what typical momentum is that relative momentum.
I mean, by looking at the Pound-K correlation.
Exactly. You get the threshold results, right?
So you can get, okay.
You could put a point, I don't know where this point is, pretty close to threshold, of course, right? But
That's good, very interesting. Yeah.
That's what the dual talk is, right?
well, for they do this for all kinds of things. I'm not surprised. They should that if the data are so bad, why they don't do pi k plus? That should be really easy, actually.
So now your question, so your fate is a curve inspired model, right?
Yeah.
So suppose I do just a linear extrapolation, actually that will go selective, right?
Right, I mean, well,
So
it depends on how you do the extrapolation.
I know. So in a sense, that's kind of prediction for curve, but we can vary in a sense, right? Because for example, if we
this is just a
curve.
This is just a like, let's say, a fit that we did to kind of make sense of the data. But ultimately, what you want to have is a lattice QCD calculation there, and we are in the process of getting that. Okay, let me move to the next topic. Otherwise, time will be eaten. And this is pion nucleon scattering and the delta resonance. So pion nucleon scattering is a very fundamental process in the description of the strong nuclear force, and in particular, pion exchange is a significant contribution that dominates multi-nuclear forces, right? And if you look at like the structure of pion nuclear scattering, you will see that this is far from trivial in the sense of like you have low-lying resonances, the first one, the delta resonance, and then you keep going higher up and you'll find other resonances like the Roper and many more. Turns out that exploring this from first principles lattice QCD is still, starting, but only now we're being able to determine properties of the resonance like the delta, which is the lowest. So in order to obtain the properties of the delta resonance, we'll need to start by determining the spectrum of QCD in this particular quantum numbers in finite volume. So we're now interested in like the isospin 3-half of a system of a pion and a nucleon. And now we do our usual lattice QCD calculation. We compute correlation functions, and from these correlation functions, we determine energy levels. Something that is very important to us is trying to make sure that the energy levels that we determine are actually stable or that the systematics associated to those energy levels are actually under control. And this is something that we do by modifying different parameters that go into this variational analysis. And this is why you see here, each of these points is really the same energy level, but has been determined in 4 different ways by varying different parameters in this variational technique. So don't worry too much about the labels of that. The important or the key message here is that by varying different parameters in these determinations, we obtain stability in the energies that we want to sustain. So now we have all these energies with statistical errors and with controlled systematic uncertainties, and then we plug it to the Flusher formalism to determine the phase shift of the delta resonance. And this is what we obtain. So I like to show these 2 plots together because I think they look very nice together. So here's the phase shift as a function of the energy of the delta resonance. The plot here on this side is experimental, and on this other side is our lattice QCD calculation. Now you can see that qualitatively, both plots look pretty similar. We have the typical feature of a narrow resonance, which is the phase or the phase shift crosses 90 degrees and then keeps going. However, this is experiments, so this is the real world. This is a lattice QCD calculation where the biomass is 200 MeV. So you don't expect these 2 plots to be identically the same, but you do expect them to qualitatively resemble each other. This is indeed what we do. Okay, so the delta resonance is it's kind of a benchmark resonance in the sense of like its properties are well under control in many ways, experimentally at least. So, but you have to reproduce it before you actually move into more complicated resonances. And this is what I want to do next. Now going to.
Can I ask a quick question?
Yeah.
So if you take the physical pion mass on the right panel,
yeah.
That means although still even now like 2 panels look similar as you said, but if we take 140, like physical pion mass on the right panel, the line is gonna be more kind of closer to the experimental result. Am I correct?
We hope so.
Yeah.
That's the hope.
Exactly. We hope
Okay.
so. Yeah.
I see.
I mean, you can see more or less. Look, so 90 degrees here is located at 100 approximately. Like 90, boop,
90.
it's like 100 more or
Okay,
less.
okay, what
And
about?
here, if you look here, 90 is at there. So it's not quantity. It's located.
Okay.
It's
Ah,
like
there,
it's not quantitatively the same
Okay.
because
okay.
there is
I
a
see.
difference in the biomass
Okay.
of about
Okay,
60
okay,
MeV.
I
So
see.
that
Okay.
that is the
Because
key
like
point.
all the Hadron Ion experiments always do the rescaling. If you do rescaling, I think it should be all.
Exactly. Probably if you rescale it, will be fine. But you know, that's not. What we should really do is go and compute it at this point. We should make sure that
Units
it's.
of the pi minus in the x-axis. But you do expect some qualitative difference because a heavier biomass is less phase space, so the delta
Yeah.
decay, so the width of the resonance will be more narrow.
Right.
Oh.
Expect that.
Yesterday we heard about the 230 of biomass and today it's 200.
Mhm.
Can we extrapolate?
In some cases, but we just not yet, not yet there. Okay, let me tell you about a resonance that is actually more interesting than the delta because it has more controversy surrounding it, and this is lambda 1405. Okay, so the lambda 1405 resonance is a resonance that has been known since the 50s, and even though it's been 70 years, it's still under investigation. This resonance appears in coupled scattering of a system of a pion sigma to a kaon proton. So you can have reactions or resonant reactions both in pi sigma to pi sigma as well as the k proton to k proton or the mixes. And here's a recent determination of GluX, the GluX experiment of photoproduction, where you can see here in the invariant mass of pi sigma, this peak just below the Kn threshold that corresponds to the lambda 1405. So why is this controversial? Well, it turns out that there's a question whether there is a single lambda 1405 resonance or whether there are like two sister resonances that are very close to each other. In particular, now this is recognizing the PDG, this controversy, in the fact that there are two resonances with the same quantum numbers that have very similar energies. One of them is the lambda 1405, and the other one is the lambda 13A. The PDG has this classification based on the confidence that we have about the resonance, and the lambda 1405 has 4 stars, so we are sure that it exists, and we know some of the properties really well. And the other one, the lambda 1380, it's just 2 stars, which means the evidence of existence is fair, which I don't even know what that means, but it just means, I guess, that it's under discussion. So why is this under discussion? Well, both experimentally and theoretically, it's a challenging process. On the one hand, experimentally, we have several experiments that have tried to or are measuring the properties of these resonances, and there are several analyses that have different results in terms of whether there's 1 or 2 resonances. We have class, Be Good, Alice, and also GluX that tell you that there are 2 different resonances, or at least that the data is compatible and the data favors the analysis based on 2 resonance poles. And we also have JPark, and that says 1 pole is more favored than 2 in their data, and a multi-experiment analysis that also says that the scenario in which there's a single pole is slightly more preferred. Okay, so we have controversy experimentally whether the data is more consistent with 2 or 1. From the theory side, there are several things that are happening. First, if we think about naive or simple quark models, this tells you that there's only room for a single baryon in that neighborhood. So there is, at least in this naive quark model picture, we only expect a single lambda 14 resonance. More intuition is gained by these so-called chiral unitarity models in which interactions between the baryons and the mesons are modeled inspired in chiral perturbation theory. And this was realized in the early 2000s, at least leads to the existence of 2 different resonance poles when the scattering amplitude is computed within this chiral unitarity approach. And this is what started this discrepancy, at least, or this controversy, at least from the theory side. Lattice QCD, at least until the study that I'm about to tell you, hadn't found a definitive answer, in the sense of like there have been studies using or investigating the lambda 1405 resonance, but no one had computed the scattering amplitude, and no one was able or had been able so far to extrapolate the complex plane and determine how many resonance poles we have. However, what I'm going to tell you is that it's our results we're using or trying to address this gap in the lattice QCD test. So the input to this analysis, as usual, is going to be energy levels. In this case, we have basically a set of 4 or 15 energies that we have determined from Euclidean correlation functions, you having different, measuring different correlation functions with different operators that look very different, like two baryons as well, two hadrons as well as a single baryon. And now here we have, the input data basically labels the spectrum that we obtained from lattice QCD, and we analyze that using the Lucier formalism, using this quantization condition that I told you about before. This requires that we assume some sort of model for the scattering amplitude, or in particular for the K matrix. Typically, the simplest thing that you can do is parameterize the K matrix in an expansion about some threshold, or something like a polynomial expansion of the energy. And you can have some parameters that you can adjust then to your data doing simple chi-square minimization. In particular, the one that is shown here as amplitude fit in blue corresponds to an analysis that has only 4 parameters that describe all 15 energy levels, and that leads to a chi-square degree of freedom of about 1. So the main result is shown now in this slide. So we use all these energy levels to constrain the scattering amplitude, and then the scattering amplitude is shown here in the upper panel as a function of the energy. So in the region between the pi sigma threshold to the Kn threshold, we can have only processes in which pi sigma goes to pi sigma, so elastic pi sigma scattering, and we have this scattering amplitude there. And then at some point we hit the Kn threshold. We have a multi-channel scattering process, but we can still determine the scattering amplitude, and we will have processes that go from Kn to Kn, as well as pi sigma to Kn, the other one. Okay. Now this is the scattering amplitude on the real axis, so this is physical scattering, but now we have to extrapolate it to the complex plane to see how many poles we find. And what we find is that, based at least in our preferred fit, there are these 2 poles here, these parameterizations these 2 poles that are found in the complex plane, leading to a virtual state just below the Kn threshold, the pi sigma threshold, and a resonance pole a little bit deep in the complex plane corresponding to a resonance. Okay? We've tried, this is just a single parameterization. We have tried many different parameterizations of the order of 20, and we have found that all of them lead to the existence of 2 different poles. The position of each pole is moved a little bit depending on what parameterization you choose, but the existence of the 2 poles is actually robust under variations of the parameterization. Okay.
So by virtual state, you mean virtual bound state?
It's a virtual bound state, yeah.
So I'm just curious, do you guys find a partner, another virtual bound state lower than this one? As in, when you have a virtual bound state, you would expect to typically have a partner of this one somewhere else lower in the same real axis.
So I would have to look again. We do see, right, so the parameterization we're choosing, we expect them to be valid in some region around where we have information, right? So we do not observe poles that are in the vicinity of physical scattering anymore. We only, sometimes for some parameterizations, we have like weird poles far away, which is, those we think there are artifacts of the parameterization. These poles, of course, have like replicas, like the resonance pole have like another pole in another Riemann sheet. So there are 4 Riemann sheets here. So some of these poles have
I meant in the same Riemann sheet, in the second one.
No, we don't see anything in the vicinity. We only see some stuff far away when they are like parameterization artifacts.
So what is this virtual bound state? Can you?
Where is the state?
Is it a bound state or not, or what makes it virtual?
So virtual bound states are poles in the scattering amplitude that do not correspond to states in the Hilbert space, in some sense. So it's a pole in the scattering amplitude. It's on the real axis in the sense of it has real energy, but it has complex momentum. In a quantum mechanical system, you can see virtual states as like non-normalizable wave functions that are eigenstates of the Hamiltonian, but they're not normalizable.
Isn't the di-neutron system?
Exactly. Like the 2 neutrons in
Well, they have a huge scattering length, but just not enough to make a bound state.
Right, but they still have a pole, and that pole is a virtual bound state.
It's attractive, so you would get a. But just the sign of the amplitude is the wrong sign. It's like a minus I instead of.
Right. So I would say, like, quantitatively, it's a pole in the scattering amplitude that is not a physical state. In the picture of quantum mechanics, is a non-normalizable eigenstate or a wave function that is an eigenstate of the Hamiltonian.
It's below threshold.
It's below threshold.
And then it's complex.
The
residue is complex.
Exactly. And
they're not complex but imaginary. Sorry.
What frequently happens with these virtual bound states is that when you vary the pion mass or the quark masses, there is kind of a smooth connection between virtuals, bound states, and resonances, and this kind of like, in some sense, like the number of poles is conserved in when you vary the pion mass, but the nature of those poles can move from resonance poles, bound states, or virtual bound states.
It's also because it's close to the threshold, or it's just rightly just a little bit below threshold.
Right. That isn't okay. So let me.
And maybe that also explains why experiment is not easy to identify. Is that right?
That is okay. So this is. Let me go to the next slide, and you'll see where I'm getting at. Okay. So where are these poles now in terms of physical values or MEV, like physical units? So what we find in this lattice QCD calculation, where I remember you, the pions are 200 MeV pions, so they're not physical pions, they're slightly heavier than physical. The first pole, the virtual bound state, is around 1390 MeV, and the other one, the resonance pole, is there with has an imaginary part because it's in the complex plane. Now, if you look into the PDG, into the analysis of the PDG, like this is what it's quoted there. This is kind of a range because there's different analysis. So in experiments or analysis to experiment, what people find is that the first pole is in this energy range, and the second pole is here. Now, if you compare that to our results, remember that our pions are slightly heavier. So what you're seeing is that our results are always a little bit above of what experimental or analysis to experimental data of experiments find. And this is something that we probably can understand as a pion mass effect. But there's also another thing that is probably related to the pion mass, and it's the fact that this pole is a virtual bound state and not a resonance pole. The moment you lower the pion mass, then this pole will more or less stay in the same position, or at least its real part will. But now the pion sigma system will be lighter. So this pole will turn into a resonance, most likely, and will be allowed to decay. So what basically will happen in experiments, or what happens in experiments, is that in some sense, going back to this plot before, this one will be somewhere here, and then you will have like this kind of feature. Okay. Yeah. But once we do have the physical point, we'll let you know if we find the stage. Yeah. Okay.
No, I'll ask later.
Okay. Sounds good. Okay. Good. So this is what I want to tell you about the Lambda 1405. The main message is, with the first lattice QCD calculation of this coupled scattering system, we have found that there are two poles, confirming the picture based on chiral unitarity models and some experimental results. Now, let's move to three-particle processes. How am I doing? Oh my God. Well, 10 minutes, I guess. Yeah.
How does people, in the PDG, they also analyze the phase shifts and so on, right, with a couple channels. Now, can they tell whether it's a virtual bound state or it's resonance? They have some, the second one is width, right?
Yeah.
The first one have no width. How does one, is it experimentally discernible whether it's virtual?
What you can do experimentally is you have your scattering, your counts per energy, and you can have a model for the scattering amplitude.
Yeah.
And you can fit your model to the scattering amplitude to what you have, like the energies on the real axis, and then that model you constrain the parameters, and then you analytically continue it to the complex plane. So it's kind of like the same that we do in lattice QCD. We have constraints on the real axis, and then you have to extrapolate away from the real axis. And then this is the same. It's fundamentally the same experiment.
Okay, fine. You have a way of doing that, changing the part masses and non masses. So, but how does the experimenter know? Given the experiment, is there ever a possibility of experimenter to know? This is about virtual bounds.
I think what experiments can do is constrain the scattering amplitude in the real axis or for real energies. I don't think an experiment can do anything else.
Well, if it's an analytic function, you measure it precisely enough, and the rest is all just mathematics.
If you have infinite precision in experiments, you will have a perfect constraint on the real axis, and you would have a perfect analytic extrapolation.
So for real resonance, of course, you can clearly say from the data, right? But for virtual, you need additional model.
To discern between virtual and resonance, really, you have to fit a model to the data and then extrapolate to the complex plane. I think there's no other way around. Okay, so three-particle processes. Why do we care about three-particle processes? Well, turns out that these two-body formalism or two-body ideas that I was telling you about are actually restricted to very few cases. There's not so many cases in QCD where you can apply illusory formalism. And in particular, if you care about exotics like the W-charm tetraquark or the Roper resonance, or like these many other resonances that are listed in the BDG, you at least need to deal with 3 particles or even more. Okay, so the first step towards that is let's go beyond 2, 3 particles. There are actually many relevant phenomena in nuclear physics or in hadron physics that involve 3-particle systems. We have the 3-body force that leads the 3-nucleon force that leads to the 3-tube nucleus, but also questions about like the nature of neutron stars related to 3-body interactions involving hadrons. And we have CP violation in kaon decays or kaon mixing that involves also 3-particle systems. Now, there's been a lot of developments dealing with a 3-particle finite volume formalism. There's a lot of people working on that, including myself, in the last few years. So let me tell you just generically how this works and then show you some results. So the 3-particle formalism is similar in spirit to the Lucier 2-particle formalism, except that now it's more complicated because we have 1 particle more in the game. So we now not only need to determine the energies that are corresponding to 2-particle systems, 2 mesons that have the quantum numbers of 2 pions or other systems of 2 particles, but we also need 3-particle spectrum. Okay. This can be obtained in principle in the same way using operators, solving the generalized eigenvalue problem, and measuring from Euclidean correlation functions. Now what we do is we take these energy levels of 2 particles and 3 particles and we pass them through the quantization conditions, the finite volume formalism. The 2-particle quantization condition you've already seen, and this analyzes the 2-particle spectrum. The 3-particle quantization condition is there too. It's more complicated, so I'm not going to go into the technical details of it. What I'm going to tell you is that the 3-particle quantization condition needs input from the 2-particle interactions, because when you have 3 particles on a box bouncing each other, sometimes 2 of the particles interact, and the third one is just looking, the spectator, right? So you need to know 2-particle interactions before you study 3-particle interactions. And then once you have that combined with the energy levels, you will access some object that we call the 3-particle K matrix. So the idea
is irreducible, the 3-particle K matrix.
The 3-particle K matrix in some way parameterizes quasi-local 3-particle interactions. Where the
Okay, so
with
it's
the 3
not
particles,
a cascade, 1 particle interacts and then with a second,
that's accounted for in this part here
okay.
somehow, and then
And this one is the
which
irreducible.
is like
Okay.
exactly.
Yeah.
It's a little more. There's a precise mathematical definition,
okay.
but qualitatively is what you're saying.
But
So-
I thought maybe I missed this though. Last time when Rahul was talking about this, the 3-body interaction, they are really just coming from 2-particle interaction. Maybe I misunderstood.
I don't think that's generally true. That might have been true for the cases that it was talked about that in that case. But in general, the K matrix is non-zero and it's different. It's different from 0 and tells you about local 3-particle interactions. And it can even be resonant. So generically it can be anything. But the idea is you have your energy levels, you have your formalism, and what you do is you take your K matrices for 2 particles and for 3 particles, you parameterize them in some form in terms of a few parameters, like 3, 10 parameters, depending on how much energy you have. And what you do is you fit this to obtain these parameters here. Once you have the parameters that describe the 3-particle and the 2-particle K matrix, you then relate K matrices to scattering amplitudes, and this is something that you might have heard actually from Rahul. The connection between K matrix and scattering amplitude for 2 particles is rather trivial, it's algebraic, but for 3 particles, it involves integral equations. This is how and this integral equation somehow makes sure that like all possible rescattering of the 2 particles are included in some way. Okay, so the pipeline is energy levels to K matrix to scattering.
Sorry, another question. Do you actually reverse? Do you get a contribution reverse error? For example, 2-particle interaction could also come in from 3-body.
No, because that is kind of effectively parameterized here. Yeah, that's kind of like that would be like hidden in the beta salpeter kernel.
Yes, that's what I mean.
And that's already hidden there in some parameterization, so you don't worry about it anymore.
Okay.
Okay, once you have the scattering amplitudes, then this is what you would convert to experiments or extrapolate to the complex plane to get amplitudes. So let me show you some results. These results are going to be for systems that are called weakly interacting, in the sense of like there are no resonance. and I'm thinking about three positive pions interacting together. There's not such a resonance in QCD that's the case in three particles. However, these weakly interacting systems are interesting to test all these techniques and to see that these three particle methods can be applied to lattice QCD. So let me show you some results. What we are doing here is we're taking our K matrix in the three particle sector, and we are parameterizing it into this expansion here with a constant plus a term K1 that is energy dependent. Okay. And now these constants here is what we are obtaining from the fits to the energy levels, and what we can plot as a function of the pion mass and things like that. So here's a plot here, the one for K0, the constant part of the K matrix. We have three different data points coming from three different lattice QCD calculations at different values of pion mass. So you can see that these points here, this one is compatible with 0, but these ones are at least significantly away from 0. And this is kind of similar picture for the other part, which is the energy dependence. Now, interestingly, there is no experimental results for three pion scattering. No one has been able to take three beams of pions and just make them scatter against each other. It's experimentally very challenging. So if we want to compare our results to something, the only guidance can come from effective field theories. That's the only other thing that we can do to tell us whether we're doing it makes sense or not. And this is what we did. So we computed the leading order KPT. This is these bands here. We saw that and we were not very happy to see that the discrepancy was pretty high. So we were like, okay, we have to go on beyond leading order. So we computed the next to leading order. And then we found these lines here. The difference between those lines is what values for the low energy constants you plug in, whether you fit them or you just take them from some papers from phenomenologic analysis. But the main point is that we've been able to determine these values, and the obtained values in lattice QCD seem to match what you expect from effective field theories. Okay, so these systems are, as I said, weakly interacting, no resonance, so they are interesting to some extent, but also boring to another extent. What we really want to do is compute three pion resonances, right? However, we don't really have a lot of data just yet. This is, lattice QCD calculations take years. So the only thing we can do is try to play with some toy models. And this is something that we did with my collaborators. In particular, we took a simple theory, which is two scalars. So imagine a 5 to the 4th theory, where you couple a heavy scalar to three light scalars. It's just a toy model. This does not resemble QCD. It's just something to test this technique. So if you allow the heavy scalar to be heavier than 3 times the lighter scalar, then you will have transitions of this form, or in some sense, you can view phi1 as a resonance of 3 phi 0. And then you can just take this, put it on a cluster, and simulate it for as many volumes as you want through Lusher or the three-particle Lusher, and then you will obtain scattering out. So here's the first plot for that. Each of these points is an energy level coming from a lattice field theory simulation of this toy model. Now this is not QCD, so you can basically simulate as much as you want and get as many points as you want. This is the energy of three particles, and you can see here a very nice feature, which is this kind of avoided level crossing. This is the typical signature of a resonance in a finite volume. So if you have resonance in a finite volume, this is the volume dependence of the energy. It will always look like two things are getting closer to each other, and eventually they never cross, but they repel. And this is really what happens with, or can be understood in a quantum mechanical picture of perturbation theory of degenerate states. But all that matters is that this is the manifestation of a resonance in finite volume. Now we take these energy levels and we map them via the formalism to get the position of the resonance in the complex plane. And this is something that we have to assume a parameterization for the K matrix. We found in this particular case that we need to add an explicit pole in the K matrix to be able to actually reproduce this resonance. And now, basically, we have a few parameters here that we have to fit to the data. And once we fit those parameters, we can solve the integral equations that I'm sure at some point Raul has told you all about. And then once you solve them, you get these points here, which are the pole position in the complex plane of this toy resonance of three particles. Something I'm not telling you about because it's just technical. There are two different ways of doing this finite volume methodology, and that's why the two different ellipses label. The key point is that even if you have different methods that look different on its face, the final result that you get for a physical value, which is the pole position, it's the same. Okay, so this is the mass and the width of that toy resonance. Okay, I still have another section, so should I?
Quickly, maybe.
Okay, I'll try to go very quickly. So that was a toy model, but really we want to care about resonances that are physically relevant. And one of them is the double charm tetrapod. It's an exotic that has been discovered at LHCb. And so going to that, this is the same picture as before. Now we have this experimental data from LHCb. This peak here corresponds to a tetraquark, to a double charm tetraquark, and is seen in the decay of this unstable exotic to 3 particles, d pi. So of course, this resonance decays to 3 particles, so we need a 3-particle formalism. But also, you can think, okay, lattice QCD gives us this tool to vary the quark masses. So we can take and say, okay, the quark masses are not physical, let's make them heavier. And then what happens is that the d star here becomes stable if you increase the quark mass. So in that particular scenario, the TCC will go into a 2-particle system. Okay. So this is something that people have tried to exploit, this usage of the Lucier formalism, forgetting about 3-particle effects to study the TCC. There's some work in that direction, very groundbreaking, where they have studied, these people have studied the d star scattering. This is the phase shift as a function of the momentum. These are points that are coming from energy levels in their calculation of lattice QCD. And this thing here, this crossing here basically tells you that there's a virtual bound state. Like this is what a manifestation of a virtual bound state in the scattering amplitude. So this looks great, except that there's a huge caveat that wasn't realized at that time, and is that this analysis is actually not formally valid. And the main reason is there are processes like this one here, one pion exchange, where you have like a U pion exchange of a DD star in this form. And this thing here is a propagator that has a pole. And that pole is located particularly in that line, which says that the formalism that you're using to map those points is not valid. A way of seeing this is that what happens effectively is that you have this one pion exchange making your phase shift complex, and that is not incorporated into the Lucier formalism. So it's, you're getting something real when it shouldn't. So unfortunately, while this was very interesting to see, this is strictly speaking not the correct thing to do, because you're neglecting the effect of one pion exchange. So what can you do instead? This is something that now we're proposing, and is to use a 3-particle formalism. So do not forget about 3 particles, even though the d star is stable. And in particular, if you have a system of 3 particles and 2 of the particles can bind into a bound state, you can still describe those as a 3-particle system. It's just there's a bound state, but there is still underlying 3-particle dynamics. And this is something that has been, Raul, among other people, have explored extensively. The idea is that this diagram here, where you have a 1 pion exchange, in the 3-particle equivalent, can be seen as this thing here, where you have kind of this diagram where the pion is being exchanged, and the d star is not seen as a particle, but it's seen as a pole in the scattering amplitude of d pi. And it's incorporated like that into the 3-particle formalism. So all the finite volume effects and all the non-analyticities and all the effects of 1 pion exchange are incorporated by considering explicitly this diagram in the finite volume, in the 3-particle formalism. Okay, so let me just skip this and tell you what is the strategy that we are proposing now to study the TCC. The idea is we have to study first 2-particle dynamics. So we will have to study the d pi scattering amplitude to get the d star either as a bound state or as a resonance. It does not matter for our case. We also need the other 2 particles in the group of 3, their interactions, like the dd interaction. Finally, we also need to add 3-particle energies and 3-particle spectrum in the form of dd pi, but also if we have a d star, we have to consider it in our interpolating operators. And we'll take all these energy levels of 2-particle systems and 3-particle systems. We will analyze with the formalism that we're proposing. I'm not telling you the details of that formalism, but we have it. We will analyze them to obtain basically decay matrices. Decay matrices of both 3 particles and 2 particles. And then we will solve integral equations. We will get the 3-particle scattering amplitude and solve on the real axis, and then extrapolate to the complex plane eventually to get the pole position of the TCC, incorporating both 2 and 3-particle effects and dealing with this 1 pion exchange. Okay, so hope that wasn't too confusing, but I'm approaching the end now.
What's the final result? You're still doing analysis.
The final result, we have the formalism. and now we need the lattice data. Yeah. So this is the formalism. The lattice data will come in the next next
Someday.
few years, I guess. Okay, so summary slide. Lattice QCD gives us a tool to investigate the hadron spectrum, not only stable particles, stable hadrons, but also unstable ones, such as the Lambda 14.5, or the delta resonance. But now we're moving into an era of three-particle scattering from Lattice QCD. So we have some results of simple systems like three positive pions or a toy model, but we kind of really want to move forward to study interesting resonances like the TCC. We now know how to do it. We just need the data to do that. So as we wait for the data, we still need to think about other stuff like formalism and things like that. But this is left for future work. Okay, so sorry for going over time, and thanks.
Have you ever attempted to study the Roper, which is a
Well,
controversy?
not yet.
I know n pi is in principle there, but the branching ratio is smaller than n pi. You just take n pi and see what anything interesting or uninteresting is coming up from
We made a proposal.
Lambda 45.
Yeah, we
made a proposal.
We have the plan to do it.
Proposal.
When we get the computing time to do it, and we resolve some of the formal issues regarding this mixing. My intuition is that probably, to some extent, three-particle physics will have to be considered, not completely neglected. Will probably need to be there in some form. So we really are working towards developing the formalism first, while we compute the lattice data to eventually have to
Bring down the states by 600 MeV from the other people's point. 600 MeV.
Yeah, okay.
It's a huge.
Yeah.
Now, the other thing is, now you have a very nice work. You have a virtual state and virtual body and this K also.
Yeah.
Now Lambda. Now, so is there a way to understand the structure of this? Compare. Let's say I was brought up in a quark model, the UDS, right? And one state and UDS and so on. In many cases, that seems to when the delta is not too bad an approximation. Right. Now, so can you tell whether this state is more like the other one is I don't know, molecular, whatever? What's the structure?
Yeah.
What's
So
the content? What's the content?
Yeah. So with the information we have so far, we cannot yet. What we need to do that is basically compute matrix elements with currents. We need to probe on the lattice. Basically, three-point function. I think it's written here, something like this, where you have like a stable lambda, you hit it with a photon, and then you produce the lambda 14.5. Things like that. You need to actually investigate those matrix elements to be able to tell anything about the structure.
Any examples of what can one expect to see, or how can you tell the difference from?
I guess. If I was given infinite computing time, infinite everything, what I would do would be figure out the way to find the Barton distribution function of an unstable particle, and then see whether the lambda, what component of the lambda is what quark, what component of the lambda is glue, and things like that. And that would be the qualitative way of computing what you're saying. But this is like a dream. This is a dream in the future.
Yeah, even a scalar now.
On the lattice, and the way to that will be to probe it to compute matrix elements of resonances with some currents.
People have suggested, of course, the tetraquark type state, whether it's a back model type, 4 quarks together, or it's molecular states. You can look at a four-point function by looking at the difference between this distance, the two quarks, quark and anti-quark, to see whether they are. So quark and anti-quark, whether this distance varies versus this distance. If it's far away, if you can tell, then it's probably molecular. Otherwise, you can just fall together.
Right.
Things like this.
I guess you can formulate that in terms of matrix elements.
Oh yeah.
And then
once a 4-point function.
And then you would just have to measure those 4-point functions somehow on the lattice and figure out how that works with Euclidean time and things like that. So I think to get there, there's some understanding of like finite volume Euclidean matrix elements that needs to happen first, but ultimately I think it's what you're saying.